In this video, we'll complete our treatment of scattering theory with the Born approximation. We'll first start by reviewing the integral Schrodinger equation, then apply the first Born approximation, then look at impulse theory and impulse approximation, and finally the Born series. So as you recall, we started with a time-independent Schrodinger equation. E psi is equal to minus h bar squared over 2m del squared psi plus v psi. And then we rewrote this using some substitutions. The first substitution was that k is equal to the square root of 2me over h bar. And the second substitution is that q is equal to 2m over h bar squared times v psi. And this becomes a driving function or a source function. So now our equation looks like this. It becomes q, which is the source function, which contains the potential, and the wave function, is equal to del squared plus k squared applied to psi. We can solve this for an arbitrary driving function, that is q proportional to our v psi, by solving for the Green's function, which is a solution for a delta function source. So if you apply a delta function source, your solution becomes g of r for the same equation as you have up here. The solution to the actual source q then becomes an integral. So psi of r, which is the solution you want up here for the full equation, is equal to the integral of the Green's function of r minus r sub 0 times q of r sub 0 integrated over r sub 0. And the Green's function solution can be expressed as a Fourier transform. That is, g of r is equal to 1 over 2 pi to the 3 halves times the integral of e to the I s dot r g of s d cubed s. So g of r is the Fourier transform of g of s, or the inverse Fourier transform of g of s. And the solution that we want is then obtained by using Cauchy's formula and contour integration. And so you have g of r is equal to 1 over 2 pi cubed, integral e to the I s dot r times 1 over k squared minus x squared d cubed s. And when you actually do the integral, you get that this becomes a spherical wave. It's minus e to the I k r over 4 pi r. The solution that we obtain in this method, that is g of r, is not unique. It's possible to show that the general solution, g prime of r, is equal to g of r plus some g sub 0 of r, where g sub 0 is any solution to the Helmholtz equation, the homogeneous Helmholtz equation, which has no driving force. So if you set the driving force to 0, or the source function to 0, del squared plus k squared applied to g sub 0 of r is equal to 0. This is the solution here at g of 0. So the general solution to the Schrodinger equation, therefore, can be written like this. G sub 0 gives you psi 0. So psi 0 is the incident wave, minus m over 2 pi h bar squared, integral of e to the I k absolute value of r minus r0 divided by absolute value of r minus r0, v of r0, psi of r0 integrated over dr0, where psi of 0 is the solution of the free particle Schrodinger equation. Del squared plus k squared is equal to psi 0 of r equal to 0. Applied to psi 0 of r is equal to 0. So in fact, that is the solution to the Helmholtz equation. Now, you have to note again here that the wave function appears on both sides of your solution. You have psi of r here, and you have psi of r0 here. These are the same function. And that means that in order to solve for this, you need to have prior knowledge of the solution, which is is a problem if you want the exact solution. But what we can do instead is use an approximation method to solve this integral equation, and it's called the Born approximation. So suppose we have a potential that's localized about a position r sub 0, which we'll set at the origin. We want to solve the integral Schrodinger equation that we had before, which is psi of r is equal to psi sub 0 of r minus m over 2 pi h bar squared integral of e to the I k absolute value of r minus r0 divided by absolute value of r minus r0. This is my spherical wave set at the origin r0 times v of r0 psi of r0 integrated over d of r0. If you're far away from the scattering center, you have that the absolute value or the magnitude of r is much, much bigger than the magnitude of r0 for points where the scattering potential is significant. That is, close to the origin or close to r0, your scattering potential is going to be something that you have to deal with, but when you're far away, it's going to be small because it drops off. And therefore, we can rewrite r minus r0 absolute value in the following way. We start with r minus r0 modulus squared, absolute value squared, and that just is r squared minus r0 squared minus 2r dot r0, where r is very large, of course, compared to r0. Well, in that case, we can ignore the r0 squared, and we have an approximate value, which is r squared. If we divide everything by r squared, is r squared times the quantity 1 minus 2 r dot r0 divided by r squared. If we take the square root, because what we want is r minus r0 absolute value, we get r times the square root of 1 minus 2 times r0 dot r dot r0 over r squared. If we now apply the binomial theorem, the first binomial expansion here, because this quantity is small compared to 1 because r squared is, r is much bigger than r0, then you get this is approximately equal to r times 1 minus r dot r0 over r squared. And when you multiply everything through by r, you get r minus r dot r0 over r. And at this point, you can rewrite r vector over r as r hat. So you have that this absolute value of r minus r0 is then approximately equal to r magnitude minus r hat dotted into r0. If we let k, which is the wave number or wave vector, be equal to k times r hat, so we have a spherical solution, then we can write for the exponential here, e to the I k absolute value of r minus r0 is then going to be using this form here for r minus r0 absolute value. This becomes e to the I k r minus e to the minus I k dot r0. And the first term, of course, is just e to the I k r because of the vector here. So the central term in the integral, this one here, could be approximated as e to the I k r times e to the minus I k dot r0 over r minus r hat dot r0. But because r is much bigger than r0, then we can ignore this second term, and we get that this is approximately equal to a spherical wave, which looks like e to the I k r over r times e to the minus I k dot r0. And if we assume that the incident wave function is given by a e to the I k z, we can take this integral equation and rewrite it as psi of r is approximately equal to a times e to the I k z minus m over 2 pi h bar squared e to the I kr over r, so that's our spherical wave, times the integral e to the minus I k dot r0, v of r0, psi of r0, dr0. So with that equation in mind, now we have to do a little bit of solution. Well, we can look at this and say, and pick out the different parts. We have the incident wave, which is A, e to the I kz. Then we have the scattered wave. And this is just like the scattered wave we had before. We have a spherical wave in the radiation zone, very far away. We have a spherical wave times a normalization constant times the scattering factor f of theta. And so A times f of theta is everything except this term here. So by inspection, we can write that f, the scattering factor of theta versus as a function of theta and phi, is approximately equal to minus m over 2 pi h bar squared a, that's the normalization constant, times the integral of e to the minus I k dot r0, v of r0, psi of r0, dr0. Now, the Born approximation we can now invoke assumes that the scattering is weak, and therefore the incoming wave is not significantly altered by the potential. So that we can write psi of r0 is approximately equal to psi 0 of r0. And that's e to the I kz0. Or A times e to the I k prime dot r0, where k prime is just k prime vector is just k in the z hat, because your incident wave is along the z direction. Now, under those circumstances, we can write our scattering factor in the following way. We can replace e to the I k dot r0 in here. So we get minus m over 2 pi h bar squared integral of e to the I times the quantity k prime minus k dotted into r0, v of r0 dr0. Because we've now replaced psi of r0 with something that looks like an exponential function. And our scattering vector is the following. We have incident wave k prime, and then the scattered wave is k, and there's a scattering vector kappa. So for low energy, that is long wavelength scattering, we can take this exponential out of the integral and write it like this. F of theta and phi is equal to minus m over 2 pi h bar squared integral of v of r dr. So for long wavelength scattering, this is the Born approximation for the scattering factor. And we'll see some examples of that later on. If the scattering is not at low energy, but the potential is spherically symmetric, so v of r vector is equal to v of r, then f of theta and phi, which is equal to minus m over 2 pi h bar squared times the integral e to the I k prime minus k dotted into r0, v of r0 dr0, becomes, with the definition of kappa is equal to kappa prime, k prime minus k, which is our scattering triangle, we can now rewrite this as kappa, and then we set the polar axis for the r0 coordinates to lie along kappa. We can rewrite k minus k prime dotted into r0 is just kappa times r0 cosine of phi. So in the r0 coordinate system, we lay the z-axis along kappa, which is a scattering vector. And under those conditions, the scattering factor now, because it's spherically symmetric, is just a function of theta alone, not of phi, and it's equal to minus m over 2 pi h bar squared, integral of e to the I kappa r0 cosine of theta 0 v of r0 squared sine theta 0 dr0 d theta 0 d phi 0. And because you can integrate out the phi 0 immediately and get 2 pi, then you have this is equal to approximately equal to minus 2m over h bar squared kappa times the integral from 0 to infinity of r v of r sine of kappa r dr. And the angular dependence of the scattering is hidden inside the kappa because that contains the theta 0. And that depends on the angle. So kappa is equal to 2k sine of theta over 2. Now in classical physics, in scattering theory we use something called the impulse approximation. This assumes that a particle keeps going in a straight line and a transverse impulse is computed to give the final scattering amplitude. So you have a transverse impulse F, a force applied for a certain amount of time that gives you the final angle. That impulse is just the integral of the transverse force times time, times dt over time. And the angle is equal to the inverse tangent, the arctangent, of the impulse divided by the momentum. So this first order correction is analogous to the first Born approximation, where the incident particle is unaffected. So this is the equivalence of the first Born approximation. If we take this analogy, we can use a series of scattering corrections called the Born series to do a more complicated scattering problem. So we start with the integral Schrodinger equation, which we know is this psi of r is equal to r hat is equal to psi 0 of r hat plus integral of g of r minus r0. All these are unit vectors. V of r0, psi of r0, d of r0 hat, where g of r hat is equal to minus m over 2 pi h bar squared e to the I k r over r. And we can rewrite this in the following way. So in a shorthand notation, we have psi is equal to the incident wave function, psi of r, psi 0, plus this integral. And that integral, I've dropped off the dr0 and so on just to keep it compact. It's g times the potential times the wave function. Now, if we replace psi on the right side by its integral representation, right, because these two are exactly the same, so if we replace this by the integral representation, we get the following. Psi is just psi 0 plus this integral. But that introduces another integral. So psi now is equal to psi 0 plus integral of g v psi 0, right? Because that's the first term. And the second term introduces a second integral. So you get integral over 2 gv times gv psi. And then you can keep going. You can have a recursive integral equation that looks sort of like this. You have psi is equal to psi 0 plus gv psi 0, that's sort of one impulse, plus a second approximation where you apply an impulse twice, again to psi 0, and then you'd have the third term where you have the impulse 3 times, and so on. And so schematically, what does this look like? It looks like psi 0, that's the first term, right? So that's an unchanged wave function. And then you add a scattering term, which involves a scattering from a center with a potential V and a Green's function G. That's this term. Then you have a second term, which involves two scattering events, and then what's coming out. And you have a third term, which involves three scattering events, and so on, and so on, and so on. And so you can go infinitely far. As long as these get smaller and smaller, then you can get a solution that converges to the exact value or close to the exact value. And this is exactly what happens in a Feynman diagram. This is how you develop scattering constants or scattering cross sections for high energy physics, where you are adding more and more complicated interactions to get a finer and finer approximation. As long as you get smaller, everything works out well.